Scientists have confirmed it. If you cross the edge of a black hole, time outside stops completely. Not slows down, not distorts, stops. The entire history of the universe plays out in front of you in a single second. What you're about to hear is not science fiction. Every word is backed by published research from the world's leading physicists. And by the end of this video, the way you see the universe will never be the same. If that already sounds insane, hit subscribe right now. Because what happens next inside that black hole is something no school ever taught you. There's a place in the universe where the laws of physics, as we know them, completely break down. A place where gravity becomes so extreme that not even light, the fastest thing that exists, can escape. Scientists call it a black hole, but that name does not even begin to describe what it actually is. It is not a hole. It is not empty. It is a collapsed point of infinite density, wrapped in an invisible boundary that marks the end of everything we understand about reality. And for decades, the question that has haunted physicists, astronomers, and dreamers alike has been simple. What actually happens the moment you cross that boundary? To answer that question honestly, we have to start at the very beginning. Black holes are born from death, specifically from the death of massive stars. When a star that is at least 20 times more massive than our sun reaches the end of its life, it runs out of nuclear fuel. For billions of years, the outward pressure of nuclear fusion has been holding the star together, fighting against the inward pull of its own gravity. The moment that fuel runs out, gravity wins. The core of the star collapses in on itself in a fraction of a second. What follows is one of the most violent events in the known universe. A supernova explosion so powerful that it briefly outshines entire galaxies. And at the center of that explosion, left behind like a scar, is the compressed core. If that core is massive enough, no force in nature can stop the collapse. It keeps compressing past the density of a neutron star, past any boundary we have a name for, until it becomes what physicists call a singularity, a point of zero volume and infinite density. A black hole is born. The nearest known black hole to Earth is called Gaia BH1. It sits approximately 1,560 light years away from us. 1 light year is roughly 5.88 trillion miles. So Gaia BH1 is about 9.18 quadrillion miles from where you're sitting right now. And that is considered our closest neighbor. There are an estimated 40 million black holes in the Milky Way galaxy alone, with supermassive black holes, objects millions or even billions of times more massive than our sun, sitting at the center of almost every large galaxy we have ever observed. The one at the center of our own galaxy is called Sagittarius A star. It is 4 million times more massive than our sun and sits roughly 26,000 light years from Earth. Now here is where it gets strange. A black hole is not simply a very dense star you could theoretically land on. It has a boundary. That boundary is called the event horizon, and it is perhaps the most important concept in all of modern astrophysics. The event horizon is not a physical surface. You cannot touch it. You cannot see it. It is defined by a single brutal fact. Beyond this point, the escape velocity required to leave exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing, no matter, no radiation, no information, can escape once it crosses that line. The event horizon is a one-way door. And what makes it philosophically terrifying is that from the outside, it is invisible. You would not know you had crossed it until it was far too late. So what would actually happen to a human being who crossed the event horizon of a black hole? The answer depends heavily on which kind of black hole we're talking about. For a stellar mass black hole, the kind born from a collapsing star, typically a few times to a few dozen times the mass of our sun, the tidal forces near the event horizon would be so extreme that your body would be destroyed long before you ever reached it. The gravity would be dramatically stronger at your feet than at your head, stretching you along one axis while compressing you along another. Physicists have given this process a name that sounds almost playful but describes something profoundly brutal: spaghettification. You would be stretched into a thin stream of particles pulled apart atom by atom, long before you crossed any meaningful threshold. But for a supermassive black hole, something on the scale of Sagittarius A star, or the black hole at the center of the galaxy Messier 87, which is 6.5 billion times the mass of our Sun, the situation is radically different. Because of its sheer size, the tidal forces at the event horizon are actually survivable. The curvature of space is gentle enough at that scale that a human body could cross the threshold without being immediately destroyed. This is the scenario that keeps physicists up at night because it raises a question with no comfortable answer. What would you experience on the other side? According to Einstein's general theory of relativity, published in 1915, gravity is not a force in the traditional sense. It is a curvature of space-time itself. Massive objects bend the fabric of space and time around them, and other objects follow the curves of that fabric. A black hole represents the ultimate extreme of this principle, a region where space-time is curved so severely that all paths through it lead inward. There is no trajectory, no direction, no choice that does not end at the singularity. Once you cross the event horizon, your future is literally encoded in the geometry of space. The singularity is not ahead of you in the way a destination is ahead of you. It is ahead of you in the way tomorrow is ahead of you. Unavoidable, written into the structure of time itself. Here is where the physics becomes almost impossible to hold in your mind. From the perspective of an outside observer watching you fall toward a black hole, something extraordinary would happen. As you approach the event horizon, they would see you slowing down. The light reaching them from your body would be increasingly redshifted, stretched to longer and longer wavelengths by the extreme gravitational field. From their perspective, you would appear to freeze at the event horizon, your image growing dimmer and redder until it faded almost completely. You would never appear across it. You would hang there, suspended for what would look like an eternity. But from your own perspective, falling freely toward the black hole, you would feel nothing unusual as you cross the threshold. In free fall, Einstein showed us you are weightless. There is no sensation of falling. The event horizon would pass over you like a whisper, and you might not even know it had happened. But here is what your instruments would show in those final moments. If they survived, the outside universe would appear to speed up dramatically. Light from distant stars and galaxies, blue shifted and compressed, would pour in. You would witness billions of years of cosmic history compressed into your final seconds of consciousness. Stars would be born and die. Galaxies would collide and merge. The entire future of the observable universe would play out before you in what would feel, to you, like no time at all. This phenomenon, the extreme slowing of time near massive objects, is called gravitational time dilation, and it is not theoretical. It has been measured here on Earth. Clocks at higher altitudes, where gravity is slightly weaker, run measurably faster than clocks at sea level. The global positioning system satellites that your phone uses to navigate must correct for this effect constantly, or the errors would accumulate to miles within a single day. Near a black hole, this effect is not a correction factor. It is total. It is absolute. Time, as experienced by an infalling observer, diverges completely from time as experienced by anyone watching from a safe distance. The question of what actually exists at the singularity, at the center of a black hole, is one that general relativity itself cannot answer. The equations produce what mathematicians call a breakdown, a point at which the values become infinite and the theory ceases to make predictions. This is generally understood to mean not that infinities actually exist in nature, but that general relativity is an incomplete description of reality at those scales. What is needed is a theory of quantum gravity, a framework that unifies Einstein's description of space-time curvature with a quantum mechanical description of particles and forces. That theory does not yet exist. Some of the most brilliant minds of the last century, Stephen Hawking, Roger Penrose, Kip Thorne, and dozens of others, have spent lifetimes working toward it. In 2015, The detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory confirmed one of the most precise predictions of general relativity and opened an entirely new window onto the universe. But the singularity remains beyond our reach, mathematically and physically. There's one more concept that must be discussed before we turn to the staggering costs of everything we have just described, and that is Hawking radiation. In 1974, the British physicist Stephen Hawking published a paper that changed the way we think about black holes forever. Drawing on both quantum mechanics and general relativity, he showed that black holes are not truly black. They emit radiation, now called Hawking radiation, as a result of quantum effects near the event horizon. Virtual particle pairs, which quantum mechanics tells us are constantly popping in and out of existence throughout space, can be separated by the event horizon. One particle falls in, the other escapes. The black hole loses a tiny amount of mass with each such event. Over an almost incomprehensibly long period of time, far longer than the current age of the universe for any black hole of stellar mass or larger, a black hole would theoretically evaporate completely. The implications of this are still being worked out. It raises what is known as the information paradox. Does the information about everything that ever fell into the black hole get destroyed, which would violate the laws of quantum mechanics, or does it somehow escape in the Hawking radiation? This remains one of the most actively debated open questions in theoretical physics today. Now we turn to the question that makes all of this viscerally real in a way that pure physics sometimes struggles to achieve. What does it actually cost to study, approach, and one day potentially reach a black hole? The most iconic image in the history of black hole astronomy was released on April 10th, 2019. It showed the supermassive black hole at the center of the galaxy Messier 87, surrounded by a glowing ring of superheated matter. It was the first direct visual evidence of a black hole's event horizon ever captured. The instrument that produced it was called the Event Horizon Telescope. Not a single telescope, but a planet-spanning network of radio observatories working in precise coordination to create an effective aperture the size of Earth. The project cost approximately $50 million United States dollars over more than a decade of development, involving over 200 researchers from 40 countries. In 2022, the same collaboration released the first image of Sagittarius A star, the black hole at the center of our own galaxy. The cost of producing that second image, including the additional observation time and computational resources required, pushed the total investment past $60 million United States dollars. But imaging a black hole from Earth is only the beginning of the financial story. The real numbers emerge when you start asking how close humanity could actually get. The nearest black hole to Earth, Gaia BH1, sits approximately 1,560 light-years away. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which reached speeds of approximately 393,000 miles per hour during its close approaches to the Sun. At that speed, traveling to Gaia BH1 would take approximately 2.4 million years. This is not a rounding error. It is not a problem that better engineering can easily solve. The distances involved are not logistical challenges. They are civilizational ones. Nevertheless, researchers and futurists have attempted to calculate what a serious interstellar mission might cost, using propulsion technologies that are theoretically possible within the bounds of known physics. A nuclear pulse propulsion system, which would work by detonating a series of nuclear devices behind a spacecraft and riding the shock waves, could theoretically achieve velocities of roughly 3 to 5% of the speed of light. At 5% of the speed of light, a journey to Gaia BH1 would still take approximately 31,000 years. The estimated development cost for such a propulsion system, based on studies conducted in the 1960s and updated with modern engineering estimates, runs between 500 billion and 2 trillion United States dollars, not including launch infrastructure, mission operations, or the generational support systems that would be required for a crew. Fusion propulsion, using controlled nuclear fusion reactions to accelerate a spacecraft, could potentially reach 10% of the speed of light, cutting that travel time to roughly 15,000 years and reducing the financial estimate only modestly, since the engineering challenges of sustained fusion propulsion are enormous. The most ambitious proposal currently being actively researched is the Breakthrough Starshot Initiative, funded with over $100 million United States dollars in initial backing from the technology entrepreneur Yuri Milner and supported publicly by the late Stephen Hawking. Breakthrough Starshot proposes accelerating gram-scale probes, each no heavier than a paperclip, to 20% of the speed of light using powerful ground-based lasers. At that velocity, a probe could reach the nearest star system, Alpha Centauri, in roughly 20 years. But Gaia BH1 is more than 360 times farther away than Alpha Centauri. At 20% of the speed of light, it would still take approximately 7,800 years to arrive. And a paperclip-sized probe, even if it survived the journey, could not study a black hole in any meaningful depth. The estimated cost to build the laser array and launch infrastructure required by Breakthrough Starshot alone exceeds 10 billion United States dollars, with recurring mission costs potentially reaching 100 billion United States dollars over the full program lifetime. The budget of the National Aeronautics and Space Administration for the fiscal year of 2024 was approximately 24.875 billion United States dollars. The entire annual budget of the agency that put human beings on the moon, that operates the James Webb Space Telescope, that runs the International Space Station and manages dozens of active planetary missions, will need to be dedicated in its entirety to black hole research for more than 4,000 years to fund a single serious interstellar mission at current propulsion technology levels. If every nation on Earth pooled their entire gross domestic product, the total value of all goods and services produced globally in a single year, which currently exceeds 100 trillion United States dollars, and dedicated it entirely to space travel, the compounding cost of life support systems, radiation shielding, generational infrastructure, and propulsion over the timescales required would still exceed any realistic projection. The economics of reaching a black hole are not unfavorable. They are, by any current measure, beyond the horizon of human financial planning in the same way that the event horizon is beyond the reach of light. What this means practically is that for the foreseeable future, our exploration of black holes will remain indirect. We will continue to improve our gravitational wave detectors. The Laser Interferometer Gravitational Wave Observatory and its international partners have detected dozens of black hole mergers since the first confirmed detection in 2015, each one carrying information about the masses, spins, and distances of the objects involved. The planned space-based gravitational wave observatory, known as the Laser Interferometer Space Antenna, with an estimated development cost of approximately 1.5 billion euros and a planned launch in the mid-2030s, will extend this capability dramatically, detecting mergers of supermassive black holes across the observable universe. The next-generation Event Horizon Telescope, currently in planning stages with an estimated cost of several hundred million United States dollars, aims to produce black hole images with 10 times the resolution of the current system, potentially revealing the detailed structure of the photon ring and the behavior of matter at the very edge of the event horizon. None of this gets a human being or even a sophisticated robotic probe anywhere near a black hole, but it advances our understanding in ways that are genuine and measurable. The physics we learn from these observations feeds directly into our theories of quantum gravity, our understanding of the early universe, our models of galaxy formation, and potentially, one day, into propulsion concepts we have not yet imagined. The history of science is filled with moments when the cost of understanding something seemed impossibly high, when the idea of decoding the human genome, or mapping the cosmic microwave background radiation, or detecting a particle as elusive as the Higgs boson seemed financially absurd. Each of those projects was completed. Each of them changed the world in ways their funders could not have predicted. Black holes are not just objects in the sky. They are questions the universe has written in the fabric of space-time. Questions about the nature of time, the limits of knowledge, and the price of understanding. We have looked at them from a distance of 1,560 light years, and captured their shadow. We have heard them collide across billions of light years in the form of gravitational waves. And we have done the math on what it would cost to get closer. The answer, for now, is everything we have and more. But the questions they raise are worth every dollar, every decade, and every generation it takes to answer them. If this video changed something in the way you think about space, about time, and about the sheer scale of what we still do not know, then you are exactly who this channel is built for. Hit subscribe right now. Every week we go deeper into the universe, the science, and the real numbers behind the most extraordinary places in existence. The next video will make this one look like a warm-up. Do not miss it.